Okie doke. Let's see. Okay, so here's an absolutely absurd, not really a compound, even absurd ion. Something with oxygen and neon. Let's see if we can work through this. So this, of course, would be a molecular orbital problem, as requested. So, again, we can ignore the 2s stuff because that's just going to be completely filled. So, let's go ahead and take a look at the P's. Let's just make both of them 1 plus. It doesn't really matter. Again, you can use either one. Neon normally is a full P, but 1 plus means it has one fewer electron. For oxygen, oxygen normally has 4 in the P. So if we get rid of 1, we're going to have 3 there. So remember, for oxygen, we're going to have the sigma 2s is going to be our lowest. Then we have pi 2, I'm sorry, 2p. These are all 2p. We got pi star. And then sigma star. So looking at this, we have, looks like 8 electrons total. So let's go ahead and start filling those in. 2, 3, 4, 5, 6, 7, 8. All right, and so if we're looking at the bond order of this, we're going to have, we have 6 bonding electrons. We have 2 non-bonding or 2 anti-bonding electrons. Divided by 2 is going to give us 2. Hooray! So that would be our bond order there. Yeah, exactly. If we're looking, we would say that this one, if we were asked, we would be able to classify this one as paramagnetic, right? We'll be able to say that as well, because we have some unpaired electrons in our anti-bonding orbital there, the pi star 2p. If we were to do the configuration of this, we would say something like this, and then pi star 2p2. Of course, the 2s stuff would come beforehand, but fine, we'll do it. That would be, I guess, the full one for the valence shell here. Let's see, what else can I ask you with this sort of thing? I don't know. If we were to look at this bond order, that would tell us that if we were to somehow create a Lewis structure between these two, it would look like this. Let's see, how many electrons is this? Oxygen is 6 using those. Actually, no. We wouldn't even need the lone pair. So that's what this horrible Lewis structure would look like. Bond order of 2 means that it is a double bond, right? I don't know. What else can I ask you about this? I don't know. Well, there we have it. So there's our disgusting, weird oxygen neon molecule, which is just foul. Of course, does not exist, I assume, unless you have some crazy like plasmas or something happening, but let's not worry. Cool. Let's see about this one. All right, let's look at this one now. Yes, Tyler, absolutely. So just throwing another random crazy molecule that I hope does not ruin everything. Let's see what we'll get. So if we're comparing more or less stable, we're looking at the bond order, right? Excuse me. So we're looking at if the bond order is higher or lower or the same. So we would go ahead and take a look at these. So let's go ahead and do it. I'm just going to do carbon 2 minus, nitrogen minus. Again, you can put whatever, you can put all 3 negatives on carbon or all 3 on nitrogen. It doesn't really matter. This is just to figure out how many electrons we have overall. So normally carbon has 2. I'm giving it 2 more. Nitrogen normally has 3, I believe. Yes. And then I'm going to give it 1 more. So it looks like we have 8 electrons total here. Remember that carbon and nitrogen have the pi 2p lower than sigma. All right, we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Oh crap, it's the same thing. Oh well, this was not intentional, but we're going to end up with the same bond order as before. Oh dear, and in fact it's going to be pretty much the same electron configuration here. Let's just throw this, let's change this. We'll make it 4 minus instead. Yes. There we go. And really just mess with this now. Okay. So there we go. Yeah, I don't want them to be the same, Kevin, so I'm going to just throw another electron in there. Because, yeah, otherwise they would be exactly the same. That was just silly, making up these crazy ions. Okay, so now that we've changed it, we can go ahead and see that the bond order is we have 6 bonding electrons, 3 non-bonding electrons. So we'll get a bond order of 1.5. And Kevin's got it exactly right. And so that would say that this is less stable than that other weird thing. Or as Kevin has written it kind of the opposite way, ONE2 plus is more stable than this CN4 minus. Okay, and then if you were to do a configuration for this, we would see it is sigma 2p 2 pi 2p star 3, and that's it. Is this going to be more or less paramagnetic than the previous one? It's still paramagnetic, right? But would we expect this one to be affected by magnetic fields more or less than the other one? Right, it's going to be less paramagnetic because there's only one unpaired electron. So, oh my gosh. than that which had 2 unpaired. It had 2 unpaired electrons. All right, so I mean, this is kind of all the stuff I can ask you about MOs, right? I can ask you about magnetic character. I can ask you to compare stability of things, and I can ask you for configurations, I guess, and numbers of paired electrons. I guess that's kind of what I can do for all this. All right, so just remember that boron, carbon, and nitrogen have pi 2p as their lowest one, and then oxygen, no, not sigma, oxygen, fluorine, and neon have sigma 2p as lowest. Okay, so just remember that for oxygen through neon, oh my gosh. Come on, tablet, you can do it. Okay. For oxygen and neon, we end up with a fluorine and neon and oxygen. We end up with a diagram that looks like that, where we have sigma at the bottom. For the other 3 that come before, we have pi at the bottom. So just remember that as well. Alrighty, okay, and then so Kevin has also asked for polar bonds. We can talk about stuff like that. And so that's gonna basically be something that just has an electronegativity difference between let's say 0.4, something around there. That's what we generally consider polar. So normally we've had what, like 30 questions and 80 minutes or so, thereabouts. For the final, it's going to be 50 questions and 2.5 hours. So you'll have more questions, but more time, and I think even proportionally you'll have more time on this. So yeah. I haven't written it yet, so who knows? That's the real question. So yeah, I mean, roughly half of it's gonna be basically 10 and 11, right? Gas laws and solutions. Throw in a couple of solids, but solid stuff again is mostly like there's not too much in the solids. So and then yeah, the other half-ish will be previous stuff. Okay, so this polarity stuff would definitely fall under where I taught it was with the I guess chapter 11. So this is definitely gonna fall under that. So anyway, so if we're looking to see if a bond is going to be polar or not, we're looking for a change or a difference of electronegativity somewhere within this range. So generally towards this end, we have something that's going to be like CH, which we are not going to consider polar. And on the other end of things, we have something like sodium fluoride, which would be ionic. So polar stuff is going to kind of lie in between those two. So anytime we're going to have a difference of electronegativity that's kind of within this range, that's what we're going to consider polar. So for example, that would be like something like these. You, of course, would be given electronegativity values if you were to need them in a problem. So if we want to take a look at these, I think I gave you guys an electronegativity table maybe in Discord. Let's see, van der Waals constants, vapor pressure, bond enthalpy. I did not give you a electronegativity table, but that's okay. Let's see. Okay, so carbon is 2.4, chlorine is about 3, H is 2.1, oxygen is 3.5. I'm just putting a bunch of these out here that I know off the top of my head, and I'll try and put some molecules with them so we can take a look at those. What else do I know? Nitrogen is about 3.0 as well. Okay. So let's take a look at some. I guess H2 should have gone first. Yeah, you did have a table on it. Unfortunately, like there are different scales people use. Just use whatever numbers that I give you. That'll be the easiest way to go about it. So, yeah. Okay, so let's look at these and see which have polar bonds and which are polar molecules. Okay, so first question is polar bonds. So, is nitrogen trichloride going to have polar bonds? Let's take a look. Indeed, we see a difference of electronegativity of about 0, so we're definitely going to say that this would be a non-polar bond between nitrogen and chlorine. At least with the numbers I've given you. If we look at the next molecule, we have two different types of bonds here. We have 2.1 and 2.4, which is 0.3. Again, you just use the absolute value. There's no negative one. It doesn't really matter. So that's going to say that CH bonds would be nonpolar. If we check the other one, that's going to say we do have a polar bond there, which is carbon-fluorine. Absolutely. NH3, we're going to see we have a difference of 0.9. So that is a polar bond. And for CO2, we have a difference of 1.1, and so that will also be a polar bond. So if we're to ask which ones have polar bonds, these three have polar bonds. If we were to ask which ones have non-polar bonds, that would be the ones that are with green. So the second compound there has some polar bonds, some non-polar bonds. So that's kind of what we're looking at there. All right, if we are to look at which ones are polar molecules, we have to look at the geometry, of course. For NCl3, we don't even have polar bonds, so let's not worry about whether the molecule is polar or not, because we shouldn't have any. If those electronegativities are going to be the same, there's not going to be any unequal sharing, so we're not going to have dipoles there. So let's look at the next one, the CH2F2, difluoromethane. Indeed, they are. So we know that the fluorines will be slightly negative, the carbon will be slightly positive, and we can very clearly see here, if we go along this line, that we're going to have some asymmetry here. And asymmetry is what leads to polarity. So this one is asymmetric. And so that means it's going to be polar. Okay, so we have polar bonds, and it is asymmetric. So it's going to be polar. If we draw ammonia, we're going to see the same thing. If we kind of like cut this in half, we see we have some asymmetry there. Remember, a lone pair is not the same thing as an atom, right? A lone pair is not the same thing as a hydrogen. So again, we have asymmetry in this molecule. Remember that trigonal pyramidal stuff, if it's got polar bonds, has to be polar, right? So definitely going to be polar there. All right, last one we have is carbon dioxide, which we've studied 15 times. And if we look at the vectors here, or if we just look at the symmetry, we'll see this is completely symmetrical. So this molecule should not be polar. If we were to draw the dipoles, we would see that they would just cancel out with each other because they're just pulling in opposite directions. I think one of them is trying to break into the food cabinet. One sec. Small one, don't be naughty. Okay, we're good. Indeed it does. That is how I would describe CO2. For sure. All right. So, we had another question on solids. Okay. Wait. Yeah, sorry, I lied, or I misspoke. So, okay, so we're gonna do some stuff here. Or, let's see. Center of negative is not C. The center of negative will be C, as well as positive. So they're going to be in the same spot. So that's why there will be it'll be nonpolar. Non-polar stuff will have theirs in the same spot. If we look at this one, we have the center of negative somewhere around here, and the center of positive is kind of on carbon. So those are not in the same spot, so that's why it's polar. Where this one, they'll, if you were to like see where the negatives are, you know, they would just cancel out with each other. So they'll cancel out, right? Doesn't matter how big the arrow is or like kind of how far it is. Because they are the same magnitude, they're going to cancel out. So it may be easier to just remember it this way. If it's symmetrical, that means your negative and positive are on the same place. If it's polar, they have it on different places. So for example, with water, we know our favorite polar molecule. We have our center of positive down at the bottom, our center of negative kind of up at the top. We get that by adding up the vectors. So we can see that the negative part is up on the top, positive part is at the bottom. Here we don't have any difference in there, so that's why it's not gonna be different. Okay, so let's go ahead and look at these. It'll be above the center atom. Yeah. Well, I mean, so if we're just looking at the dipoles, if we add those up, we get one that is like this. If we add these two up, we end up with something like this, right? And so that's why the center of negative part is going to be a little bit higher. So a little bit higher than the oxygen, technically. And the positive will be a little bit lower than the hydrogens. So that's why. Okay. But that being aside, identify these for me. Which one is the conductor? Which one is the semiconductor? Which one is the insulator here? Oh my goodness, did we bamboozle Kevin? Yeah, if your thing were upside down, it would just be the opposite. Are you sure about your answer, Kevin? Middle is insulator for sure. This one's actually the conductor. There are overlapping bands. So it will conduct at all times. Since the conduction band and the valence band overlap, electrons can just easily flow between the two, no problems. And so the semiconductor is going to be the one on the left. That's going to have the small band gap, right? Insulators would have a large one. And conductors would just not have any band gap. So, I mean, technically, your semiconductor could look like the conductor one if it was at really low temperatures or something, or if there were special conditions. But if you had to assign only one name to the one on the right, it would be conductor, right? Because we would want everything to overlap. Does this make sense? Get out of here with your superconductors. Those are special ones that have even more overlap. So, not something covered in the course, Shane, so don't worry. But yeah, those would just be even more overlap. Especially, again, superconductors really work well at low temperatures. So, because you have a lot of what's the word? You know what? Forget it. Don't even talk about superconductors. Don't worry about them, Shane. Okay? So easy. We will not worry. Alrighty. I guess really the only other thing we talked about with solids Remember, I'm not asking you any more geometry stuff because that took forever. And we don't really need to do that ever again. Let's just, let's see, what... Okay. I can fit all of this. Yes. So, we had 4 types of solids, right? Hopefully we remember those. And we kind of also have 4 reasons that something would be solid. So, let's take a look at these. Which type of solid corresponds with which type of bonding? I guess I should tell you what the types of solids are because we probably have forgotten. We have molecular solids. We have ionic solids. We have metallic solids. And we have network solids. Those are the 4 types of solids. So let's see if we can assign these to their proper categories. Perhaps one of these is super easy to identify which one it belongs to. Let's see if we can assign one of them right away. Very good, Tyler. Well done. Oh no, you spelled it wrong. I have to take off points. Okay, 1 down. Yeah, right. Here it comes. How did you spell it? Metlic. Okay, so there we go. There's Tyler. Kevin has already done everything. Oh, and I may have, yeah, right. I may have bamboozled Kevin again, which is awesome. Okay, so yes, ionic for sure will go in the electrostatic box. However, Kevin, I think we have perhaps forgotten the vocabulary here. So network solids are going to be like diamond, whereas molecular ones would be like ice or sugar. Those would be examples of molecular solids. So if we take a look at those, this is our diamond, right? Actually, this is a really ugly diamond, but oh my god, and I have a carbon with 5 bonds. Oh no, nobody saw that. Okay, good. I hope I don't have any more. No, we're good. Right. So, and this just goes on forever, right? Pretty much. These just keep going to other carbons. This would be an example of a network one. Do we see any intermolecular forces happen? Yeah, exactly. Kevin is the new snail now. For a network solid like this, we are only going to have covalent bonds. Oh no, I'm the snail, prof. Oh no. How did this happen? Oh, because of the 5 carbons, I see. Very well. Sad times. So these are going to actually just have covalent bonds. And so we're going to see that this is where our network solids are going to be. The IMF ones would be what hold molecular solids together. So if, for example, water... if we want these to be solid, right, they're going to arrange themselves in nice little crystals. And so that's what's going to be holding these together is the, in this case, hydrogen bonds between them. That's going to hold these things in place, and they're not going to be able to float around each other at low energies. So, below 0 degrees Celsius, our water molecules will be locked into these sort of crystals in the solid form, held together by their hydrogen bonds. And remember that hydrogen bonds are, of course, intermolecular forces. And that's what's going to be holding those together. So that is going to be a molecular solid. So I guess it would be a good idea to kind of just remember one representative structure for each kind of class here. So for an ionic solid, you could think of sodium chloride. That's a pretty standard ionic compound. You could be, oh, that's right, that's made of positive and negative. Those are ionic things, and those are electrostatic forces holding them together. Positives and negatives interacting together. Network ones, you'll probably want to think of diamond with carbons that only have 4 bonds, like so. For molecular ones, I think ice is a good one to think of, so you can remember the hydrogen bonds that are hanging out between them. But we're going to see a lot of them are molecular solids. That's kind of one of our biggest classes. So like all of our organic compounds are like mothballs and all that stuff. Those are just non-polar molecules. They are just held together by van der Waals forces. That's it. Metallic solid is the easiest one, of course. Whatever, think of copper or something like that, where you just have one, simple metal. Graphite would be another example if you wanted to think of another network solid. Mothballs are dichlorobenzene. Paradichlorobenzene, in fact. Completely non-polar, right? As we can see in this lovely diagram I've drawn, we have perfect symmetry. Symmetry means non-polar, right? These would interact together through intermolecular forces. So there are not covalent bonds holding together these molecules. I mean, of course, intramolecularly there are covalent bonds, but if we were to take another molecule of it, there are no covalent bonds in between these two molecules. They would be able to interact through London dispersion forces, though in fact you'll see in OChem we have another one called pi-pi stacking, but let's not worry about that. This would be another example of a molecular one. They're just kind of there by just interacting through London dispersion forces. I mean, worst comes to worst, we can just look at the other 3 and know it's not one of them. We do not have any covalent bonds between these 2 molecules, so it's not a network. There are no positives and negatives there. It's not electrostatic, and it's definitely not a metal, so it's got to be molecular, right? Uh, and in case you don't know, mothballs are what old people used to put in their like dressers to prevent moths from going there, because these stink. This molecule stinks, and so it deters moth larvae from eating your clothes. So, and it's pretty stinky, so people would smell like mothballs. But yeah, that's a little bit off topic, but that's okay. So really, anyways, back to this stuff. Kind of the only things you should focus on for 12 would be the types of solids, and then this kind of idea here. That's it. So don't worry about the crystal structures and the unit cells. Don't worry about the polymers, or stuff like that, or the alloys. Focus on these two things, okay? I know, that's why I'm here too. So okay, let's see. Is there anything else we'd like to go over, or do some more of these, or what would we like to do? Periodic trends, huh? Okay. Let's see, what shall we ask about those? What topics do we even have in that chapter? That's the real question. Okay. So we had size, we had electron affinity, all that sort of thing. Let's pull up your exam from that, so we can maybe do some questions off that. But also to see what the heck the topics were. Oh wait, that's chapter 7, yeah. So let's take a look at the chapter 7 homework actually, and see what sort of fun stuff we can come up with there. I mean, were there any like specific trends you wanted to go over, or like, I mean, we can compare some random stuff. Just a refresher. All right, so let's compare the sizes of these three. Which one is the biggest and why? And which one is the smallest and why? For that very same reason. I would agree. Why? Lost electrons, And so how does that make it smaller? Exactly. So we have less electrons, and so we have a greater effective nuclear charge, right? So, and because the other electrons would be attracted to the nucleus, they're going to shrink down and go on that. So, absolutely. Okay, so Kevin has said the neutral one, which I'm just going to put the 0 just so we see that it's neutral, is going to be the largest. that one has the most electrons, and so most repulsion. We could also say that's the smallest effective nuclear charge, right? Because all of those electrons are competing for like the attention of the nucleus, as it were. So they're going to repel each other as well. So you're going to end up with a bigger atom as a result. All right, so that's good. Let's see, what else do we have in these topics? In terms of periodic trends, what kind of like trend are we displaying here, or like what type of? There's an enthalpy associated, right, with this, whatever it happens to be, whatever. What would we call this delta H for this one? Yes, very good. That's what I'm looking for. Yeah. So this delta H is going to be the electron affinity for iron 3+. How about this one? What would the delta H be called for this one? Let's be super specific, since we do have a name for this particular one. It is an ionization energy, but what ionization energy? Is it the first one? I would say, yeah, it's the third ionization energy. The first one would just be this would be the first ionization energy. One S plus. Wow. Okay. That one's the first ionization energy, yes. So this one would be the third ionization energy of iron. Yep, I know. We always do that, right? So, yeah, so that would be the third ionization energy. Because that is the third electron it's losing, right? Let's see, what else can we do? Yeah, we could do a guess law. Let's just do one or two more periodic trends. Ooh, depends, Shane. Sometimes yes, sometimes no. I mean, if you're just looking at like to lose one electron versus losing 3 electrons, yeah, losing one is always less energy. But if you're comparing the first ionization to the second ionization or to the third ionization, things get more hairy. So just like the difference between this one, the Fe2 plus going to the third versus the first, the magnitude of the third is probably less because iron 3 plus is particularly stable, but let's not worry about that. It is always less energy to lose one electron than it is to lose multiple. However, if you've already lost some electrons, it may be easier to lose more than if you were neutral, losing one electron. So let's not get into that. Kind of, yeah. I remember there was that kind of we have these like periods where it's more stable. Yeah, exactly. So when we have the half-filled subshells for the Ds or for the Ps, remember that like for nitrogen, we have a particularly like happy place for it to lose an electron, and then it goes crazy because, yeah, all that crap. Let's look at this one instead. Let's not worry about that anymore. Is this thing going to be acidic or basic? Right, and it's going to be acidic for sure. And we know that because it is a non-metal oxide. And if we were to combine it with oxygen, I meant water. We would get selenic acid. And so that's an acid, right? So that would be what happens there. Remember, metals are basic oxides. Non-metal oxides are acidic. Okay. Cool. Okay, so I think she wanted to do a gas law problem. That's a pretty big chapter. Is there like a particular? Yeah, I heard that as well. Did you guys hear that on the stream, or was that just outside? Anyways, let's see. Oh, it's both. All right. Well, then, with the gas laws, yeah. What type of thing did you want to do with that? Because we probably only have time for like one problem. So if you want to talk about something with like density or ideal gas law or homework 30. Okay, we can do that. Let's go ahead and look at the gas law homework. Okay, number 30. Let's go ahead and open this up. Number 30 is this one again. Okay, so this is not one I would worry about. Because I mean we can do this, but all right. So number 30 is asking us to own up to our negligence. That's okay. Yeah, we can do it. So it says that neon has a radius of 0.69 angstroms. What fraction of space do neon atoms occupy? Okay, so here is our container. Our container is, let's just say, 22.4 liters. That's a nice number for us. And we have we know for 1 mole of neon at STP, we have these two numbers, right? We know that would occupy 22.4 liters, and we know that 1 mole is that many atoms of neon. And so we're trying to kind of basically compare the volume of all these atoms to the volume of the container, which the gases would occupy. So we know that the volume of the container is 22.4 liters, right? At 1 mole, that's how much a gas occupies. So if you were to put 1 mole of gas into and you wanted it to be 1 atmosphere at 0 degrees Celsius, the container would have to be 22.4 liters. Otherwise, your pressure would be different. So to make this work, it has to be 22.4 liters. Okay, so if we are comparing the volume of the atoms, we know that the volume of one atom is 4/3 pi r cubed, right? We're assuming they're spherical, which is a pretty good assumption. And we know that we have this many atoms in there, right? We have 1 mole. And so this just comes down to getting this to work out mathematically. So let's see, angstrom is 10 to the 10 meters, so this will be 10 to the negative 11 meters times Avogadro's number. Doing this, let's see, 4/3 times pi times 6.9 to the negative 11 cubed multiplied by Avogadro's number. Okay, doing all this, I got 8.2866 times 10 to the negative 7 meters cubed. Okay. So technically this is meters cubed times a mole, or actually no, it's just atoms. Never mind. So we're going to want to convert this to either liters or convert our liters into cubic meters. We can just do this one. Remember that 1,000 liters is 1 cubic meter. Doing this math, whatever it's going to end up being, gets us this really small number. What the fraction of occupied? It's going to be, I can't even count all these zeros. Or, okay, let's just do it. 0.0000370. Something like that. That would be your answer. I don't think it asked for percent or anything, but, or if it did, we can do that. What fraction? So that's it. So that would be your answer. But again, this is not really a representative problem of what you would find on an exam. This was more just a like, what happens, what's the like, is it a safe assumption to get rid of the volume of the atoms? And yeah, it kind of is. This is a very small fraction. It's not really going to change our answers very much. So that's it. Let's see. So if we're looking at the homework problems, let me look at the key, because I think that'll be the fastest way to check that. Gas loss key. So, I mean, really anything that has our PV equals nRT would be, you know, a very nice problem to have. So, like, 33 was a good one. That was just the chart where you fill in the missing one. Something like 37 would be a good one. 40, 51, 55, 56, 57, 63, 64, 70. So basically it's just the ones, actually, yeah, it's basically everything after, it's from 33 to the end. Those would be kind of more representative problems. So like the stuff with like converting between inches of mercury and torr, like I don't really want you to worry about that because that's kind of silly. But like all the stuff involving the ideal gas law, Van der Waals law, Dalton's law, and Graham's law, like all those are fair game. Yeah, speed would be kind of with Graham's law, yeah. Yeah, take it. Take it, Tyler. Click it, take it. 2 questions. You have unlimited tries and unlimited time. So go ahead and take it. You'll see. I mean, I guess I can show you. It doesn't really... Yeah, right? Okay, where are we here? Let's take the quiz. Aha! 2 questions. What did you do? And then were there problems with your group? Did Kevin completely hijack all of the work and not allow you to do anything? You know, that sort of question would be so complicated. So there you go. So this is where everybody, all your other group mates can say, you know, Tyler really slowed us down. You know, we couldn't get anything done. We just had to meet without him. That's where that sort of thing would go. And so that would affect Tyler's grade, of course, if everyone says he was just the worst partner ever. And yeah. So we'll see what Kevin has to say about you. So yes. I hope that is not feeding Kevin the answers there. So, but anyways, yes. Okay, so that's the individual lab thing. Okay, so go ahead, put more questions that we can go over on Monday. Hooray. Beg Kevin for mercy. I see how it is. So, yeah. Okay. Well, with with that, I'll see you guys on Monday. So have fun. Have a nice weekend. Don't forget to submit your projects. Yep, of course. And then put more questions for Monday. We'll go over some more. And then we're done. Alrighty. Yep. Take care.